in practice, especially when we use deep learning, deep neural networks, the sampling complexity theory, the VC dimension and PAC learning theories, what we have discussed until now, is not good explanation for the performance of the machine learning algorithms. Recently, I cannot find any researchers who explain the deep learning performance using VC dimension. It is very difficult, or it's not a good direction to explain deep learning using VC dimension or PAC learning sense. Why there is such a gap between theory and practice? The first reason, I think, is we do not learn ERM, empirical risk minimization. Instead, we first randomly select the initial point. So we start from random initial point. And then we learn our algorithm using SGD. We find better parameters. So from the random initial parameters, we iteratively update our parameters so that the parameter can have better training performance using SGD, stochastic gradient descent, which is very stochastic property. And then we end the SGD process at some point. Okay, because we do not want to minimize the training loss among entire parameter space. We just learn SGD and stop at some point. We cannot guarantee the end point is the minimum point. So we basically do not find this L set as the loss function with respect to the parameter. We do not find this solution. We just learn some gradient descent step several times and then stop. And since we use stochastic gradient, we actually do not use the exact gradient, but instead we obtain some stochastic gradient of which expectation value is equal to this. Anyway, the main point is this. We randomly initialize the parameter and then learn SGD and stop at some point, which does not guarantee the minimum point of our loss function. We do not learn ERM rules, so all the explanation based on ERM cannot be applied to our deep learning training process. And the second reason, I guess, is even with ERM, when we have very complicated algorithm, very flexible algorithm, there could be bunch of solution, right? ERM rule can have many or infinitely many different solutions. All these parameters, all these models defined with these parameters can have zero training error. Indeed, when you train CIFAR-10 using complicated neural network, you can find infinitely many different parameters that can have zero training error. Okay, there are huge size of zero training error models, but our theory, our VC dimension and PAC learning theory, in the proof, we consider the worst case hypothesis among ERM solution. Okay? If there exists any tiny amount of a bad hypothesis that has zero training error, the worst case decide our PAC learning theory and VC dimension theory. But So in our theory, in our proof, we want to make the sample size so that the ERM solution exclude any, any, exclude any worst case scenario that has a high test error. So we want to increase the training set size so that the ERM solution shrink and the solution can exclude the worst case area. But when you think the training process of deep neural network, we first randomly initialize and then learn SGD and stuff somewhere, which basically randomly shot some our arrow, and then the location of this arrow will be our solutions, kind of. This random selection, basically, when you have this tiny amount of worst case scenario having high test error, with very high probability, our solution will be good because this area is very tiny. Your random choice will give you very nice solution with high probability. Okay, so the worst case scenario analysis make our required sample size much more than what we really need in practice. Okay, and the certain reason why the practice many very complicated and flexible neural network can have very nice generalization performance. So consider binary classification case. We have a circle and cross class. Here, intuitively nice boundary having very nice generalization error will be like this. But one concern for very flexible algorithm is the flexible algorithm can have infinitely many solutions, and this kind of very wiggly boundary can also be a solution. And so because of this kind of boundary, it is expected to have high generalization error like this area. But in practice, when we learn deep learning training process, we basically have regularization techniques. That is another magic why we can have very nice generalization performance. For instance, we use L2 regularization, that is also called weight decay. So instead of just minimizing your loss, we additionally consider some 2-norm scale of our parameter vector so that our parameters have very nice shape. Nice shape means bad shape means some parameter has huge value, some parameter has very tiny value. Then such parameter distribution with high chance such very wiggly boundary. But when we make every parameter share a similar value range, from experience, we know that the boundary becomes very smooth. So this additional cost term, which is called a regularization function or cost function, that can make our boundary more smooth and have better generalization performance. Another example of regularization is very famous dropout or batch normalization. All these techniques also make your parameter space becomes more smooth. Dropout basically train your model by randomly erasing some parameters so that your training model can fit your training data even if you randomly remove some part of your algorithm. Then your final outcome becomes robust to such random erasure, which can make your boundary more smooth. Batch normalization randomly gets the batch mean and batch variance. That can also make your algorithm to be robust to such a random guessing noise, and that robustness make very nice generalization performance.